One key driver in the modern automated manufacturing industry is the demand for highly customized, highly complex products at a batch size of one. As the requirements for customization become more customer-driven, the precise product configuration may not be known in advance. We have therefore developed a tool for addressing the problems of manufacturability and control in an adaptive evolvable assembly system. In our multi-agent architecture, each manufacturing resource is represented and controlled by an agent. Any agent in the system can receive a production recipe, which then synthesizes a controller for it and executes the controller by orchestrating other resource and transport agents. The example we will use is our precision assembly demonstrator, which we have used to assemble hinges for commercial vehicles. Resource tabs are used to model the production and transport resources in the manufacturing system as labeled transition systems. This production resource models the behavior of the two robotic arms. This production resource models the behavior of the testing station. The transport system, for example a conveyor belt or shuttle system, is also modeled as a resource and specifies the valid routes between production resources. This transport resource describes the behavior of the shuttle system. The recipe tab is where the product to be manufactured is displayed or procedurally generated. Recipes can also arrive as queries from external sources, asking whether the product modeled can be manufactured. Like resources, recipes are modeled as labeled transition systems. This recipe specifies the operations and the manipulation of parts needed in order to manufacture a hinge. States are drawn by double-clicking and editing the default label if necessary. And once a transition is drawn, its label is edited to specify the sequential and/or parallel operations that need to be performed on parts. For example, this transition label specifies that a fresh pallet or fixture F should be loaded, after which it should be separated into pin P and hollow hinge H. Syntax errors in the operation specification are indicated at the bottom of the screen. For example, forgetting to specify the output parts in the separate operation causes a syntax error. The tool also supports other features such as graph validation, selecting and moving nodes at once, and keeping graphs auto-arranged. We use the industry standard Business to Manufacturing Markup Language, or B2MML, to control our manufacturing hardware. Right-clicking on a resource transition allows creating or editing its operations template. Some of the fields are filled in later by the tool. This template for the separate operation defines additional fields detailing the specific gripper to be used and the parameter types, such as fixture and pin. Since all the resources are now modeled in the tool, we can compute the topology of the manufacturing system, which connects the available resources and represents the layout of the production system. This process may take a long time, but only needs to be done once or infrequently. This particular topology is quite large and consists of over 2,500 states and transitions in total. By zooming in, we can examine the finer details, although this would not normally be required of an operator. We can now check whether the hinge can be manufactured on this topology or whether the production recipe is manufacturable. Manufacturability is indicated by the green signal at the bottom. If we now display the resulting controller, we can see how the modeled production resources should be orchestrated in order to manufacture the product. In this example, the first transition in the controller states that in order to realize the recipe's first transition, which specified a load and a separate, the first resource should load a fixture, transfer it to the fifth resource, the shuttle system, which should transfer it to the second resource, which can then separate the fixture into its constituent parts. The states that you see represent the states in the recipe, combined with the corresponding states in the resources and the parts being worked in these states. The controller can also be visualized as an industry-standard B2MML operations schedule. An operations schedule is an and/or tree of B2MML operations requests, which includes information that is automatically extracted from the controller, such as the equipment or resources required. For example, the first operations request corresponds to the load operation in the controller. The second corresponds to the transfer of parts from resource 1 to resource 5. And the fourth corresponds to the separate operation, which the controller had allocated to the second resource, the robot arm. The choice point at the end of the operations schedule represents the choices in the controller. We can now go back to the recipe and alter one of its transitions. In this case, we request a force test to be performed on the pin soon after glue is applied to it. The recipe is no longer manufacturable. This is because, for safety reasons, our shuttle system, and therefore the resulting topology, does not allow glued parts to be sent to the testing station. This is to prevent the part becoming stuck to the force testing actuator. Thank you for watching.